So, good morning everyone. Today we are going to discuss about module 4. So, in module 4 consists of majorly instruments, then the generalized configuration of instruments and their functional elements, then the classification of instruments, then the static and dynamic characteristics of the instruments, then measurement of resistance using resistance bridge, inductance using Maxwell's WEIN bridge, and capacitance using SCHERING bridge. So these all are the things that we are going to see today. So first, the generalized configuration of instruments and the functional elements. Okay. So here you can see the block diagram. Initially, a physical quantity is to be measured, and that is fed as an input to a primary sensing element. And the primary sensing element, it will be converting into a desired form, electrical or mechanical, whatever form we required, and it will be converting and fed into a variable conversion element. Okay, and this variable conversion element is an optional element. Sometime it will be present, sometime it will be not there. It is based on our requirement. It will be converting into a more desired form, the input signal into a more desired form, and from there it is fed to a variable manipulated element in which it will amplify the magnitude or frequency have to be changed, means it will change the frequency. So it will be manipulating the input given by primary sensing element or the variable conversion element, and it will be amplified and fed to a data transmission element. And this data transmission element, it will transmit the data, and it is given to a data processing element, and this data transmission is present in every module. From one module to other module it will be transmitting. Okay, so it will be present everywhere also, and the transmitted data will be coming to data processing element, and this data processing element, it will be comparing with a standard value, and it will process data, and it is given to data presentation element. In data presentation element, data will be in a readable format, and the observer can read the data from the data presentation element. So this is about this block diagram, and we will see in detail. That is, the primary sensing element is there. So the primary sensing element receives signal of a physical quantity to be measured. It converts the signal to a suitable form, electrical, mechanical, or other forms, so that it becomes easier for other elements of the system to either convert or manipulate it. And second one is variable conversion element. Variable conversion element converts output of primary sensing element to a more desired form or more suitable form. This element is used only if necessary. Then variable manipulation element, it manipulates and amplifies the output from variable conversion element or primary sensing element, and also it also removes noise present if present in the signal. Okay, it also changes frequency required. And data processing element, it is the most important element used in measurement system. It processes the data signals received from variable manipulated element or data transmission element and produces suitable output. It also compared the measured value with the standard value to produce required output. Then data transmission system, it is used for transmitting data from one element to other. It acts as a communication link between different elements of the measurement system. Some of the data transmission elements used are cables, wireless antenna, transducers, telemetry system, etc. Okay. Next one is data presentation element. It is used to present data. It is used to present the measured physical quantity in a human readable form to the observer. It receives processed data from the data processing element and presents the data in the human readable form. Some LED display. Okay. So these all are about that block diagram. And also in addition to that, in addition to the mentioned component, the instrument might be also having a data storage element to store the measured data for future use. Okay, it will be also having a data storage element for storing the measured data for future use. Okay, Next one is classification of instruments. Instruments can be classified into different types. One is general classification, then based on instruments characteristics, based on calibration required, based on nature of instruments, then based on method used for measurements. And each classification we will be discussing here. Okay, first one is general classification. General classification can be divided into mechanical instruments, electrical instruments, and electronic instruments. First one is mechanical instruments. It is very reliable for static and stable operation, stable conditions. Okay, the major disadvantage here, it cannot respond rapidly to measurement of dynamic and transient condition. For static condition it is okay, but in dynamic condition it can't respond fastly. Okay, so that is disadvantage of mechanical instruments. Next one is electrical instruments. Electrical methods indicates outputs of detectors are more rapid than mechanical methods. It depends upon a mechanical meter movement as indicating device. For example, a meter. It will be having a mechanical meter for measurement. Okay, that is electrical instrument. Then electronic instruments have very fast response. Electronic instruments are having very fast response. Example, CRO is capable to follow dynamic and transient changes of the order of few nanoseconds. So these electronic instruments are very faster, and it is faster for both static and dynamic operations. So these are the general classification. Next one is classification based on instruments characteristics. Okay, based on instruments characteristics. That is, one is active and passive instruments. The quantity in active instruments, the quantity being measured modulates the magnitude of some external power source. Okay, there will be external power source, and the quantity being measured will be modulating that. Example, float type petrol tank lever indicator. Okay, the change in petrol level moves a potentiometer arm, which changes the proportion of external voltage source applied. That is active instruments. In that, the measured quantity will be modulating a magnitude of external power source. Okay, and in passive instruments, output is entirely produced by the quantity being measured. Example, passive pressure gauge. Okay, then null type and deflection type instruments. First we have discussed about active and passive instrument, then null type and deflection type instruments. In null type instruments, the value of the quantity being measured is displayed in terms of amount of movement of a pointer. Example, passive pressure gauge. Here the value of the quantity is displayed in terms of the movement of pointer. Okay, example, passive pressure gauge. Accuracy of the deflection type instrument depends upon linearity and calibration of the spring. Okay, accuracy is depending on the linearity and calibration of that instrument. Okay, here the value of the quantity measured will be indicating by the pointer. Okay, and null type instruments, 0-volt null indication determines the magnitude of the measured quantity. It uses a null detector. You have heard about null detector. It uses a null detector which indicating the null condition when the measured quantity and the opposite quantity are same. Two quantities will be there. When the measured quantity and opposite quantities are same, this null indicator will be pointing to 0. Okay, null type instruments are more accurate than deflection type in general. Example, dead weight pressure gauge. Okay, next one is analog and digital instruments. Analog instruments gives output that varies continuously as the quantity being measured changes output, and it will be having infinite number of measurements or values within the range. Example, deflection type pressure gauge. Digital instruments indicate the value of the measurement in forms of numbers, or to be very precise, decimal or hexadecimal numbers. Example, digital thermometer. Here the major example you can see that analog and digital weight meter. In analog weight meter, it will be continuously varying quantity. Okay, when the output is measuring, and it will be having infinite number of measurements in between them. In digital instruments, you can see the in digital weight meter, um, you know that it will be measured in terms of numbers. Okay, output will be measured in terms of numbers, or with the decimal places also it will be there. Okay, so these are analog and digital instruments. Next one is classification based on calibration required. Okay, on the basis of calibration required or not required, the instruments are classified into absolute instruments and secondary instruments. In absolute instruments, instruments that give magnitude of the quantity being measured in terms of constants of the instrument. Okay, for example, tangent galvanometer. In that, it measures current in terms of tangent of the angle of deflection produced by the current, radius and number of turns of the galvanometer, and horizontal component of earth magnetic field. So here the instrument that give magnitude of the quantity be measured in terms of constants of the instruments. Okay, and in secondary instruments, deflection of deflection of such instruments directly gives magnitude of the quantity being measured. Okay, it will be giving magnitude of the quantity that being measured. Here, in the case of absolute instruments, it will be giving magnitude of the quantity that measured in terms of constant of the instruments. Okay, that is a major difference. So here, um, in secondary instruments have to be calibrated by comparison with a absolute instrument or with another secondary instruments which are already calibrated. Such instruments are commonly used in laboratories, industries, power stations, etc. Okay, these are about absolute and secondary instruments. Next one is classification based on nature of instrument. Based on nature of instruments, instruments are classified into indicating instruments. These instruments gives magnitude of quantity at the time when it is being measured. Okay, it will be giving magnitude of the quantity at the time when it is being measured. The measurement is indicated by a pointer moving over a marked dial. Okay, example voltmeter, ammeter. These are indicating instrument. Next one is recording instrument. These instruments gives continuous record of quantity being measured over a given period. The variation of the quantity measured are recorded by a pen. The inked pen lightly touches a paper wrapped over the drum. The drum rotates slowly at a uniform speed and the pen is deflected by the magnitude of quantity being measured. This curve is traced. Example ECG. ECG യിൽ എന്താണ് ചെയ്യുന്നത്? അതായത് നമ്മുടെ ഹാർട്ട് ബീറ്റും കാര്യങ്ങളൊക്കെ മെഷർ ചെയ്യുന്ന അനുസരിച്ചിട്ട് ഒരു പെൻ ഉണ്ടാവും. ആ പെൻ ഒരു പേപ്പറിൽ അതിനെ കറക്റ്റായിട്ട് മാപ്പ് ചെയ്യുന്നതായിരിക്കും. ഓക്കെ, ആ ടൈപ്പ് ഇൻസ്ട്രുമെന്റ്സിന് പറയുന്നതാണ് റെക്കോർഡിംഗ് ഇൻസ്ട്രുമെന്റ്സ്. ഓക്കെ, നെക്സ്റ്റ് വൺ ഇസ് integrating instruments. These instruments gives total amount of quantity being measured over a given period of time. It will be giving a total. Here it is recording instantaneously or continuously in recording instruments. In the case of integrating instruments, these instruments give total amount of quantity being measured over a period of time. Example, ampere hour meter, odometer in cars, etc. Okay. Next one is classification based on method used for measurement. In that, direct measuring instruments are there and comparison instruments are there. In direct measuring instruments, it converts energy of the measured quantity directly into energy that actuate the instruments, and the value is measured or displayed or recorded directly. They are simple and inexpensive. Example, ammeter, voltmeter. Okay, it will be giving direct data. Then next one is comparison instruments. It measures a unknown quantity by comparison with a standard. Okay, example DC bits, AC bits, potentiometer, etc. And these are used for higher accuracy of measurements is required. These are used when a higher accuracy of measurement is required. Okay, these all are the classification of instruments. Next one, we will see the generalized performance characteristics of instruments. To select an instruments, the performance characteristic of that instruments must be known and it should be compared with each other. The performance characteristics of instruments are divided into static and dynamic characteristics. What is static characteristics? Okay, performance characteristics which measure slowly by varying or unvarying data and thereby indicate the response of the instruments are known as static characteristics. Okay, ഒരു ടൈം ഇൻസ്റ്റൻറ്റിൽ അല്ലെങ്കിൽ നോൺ വാരിയിങ് ഡാറ്റ അതിൻ്റെ മെഷർമെൻറ്റും അതിൻ്റെ റെസ്പോൺസ് എടുക്കുന്നതും കാര്യങ്ങളൊക്കെയാണ് സ്റ്റാറ്റിക് ക്യാരക്ടറിസ്റ്റിക്സിൽ വരുന്നത്. സ്റ്റാറ്റിക് കാലിബ്രേഷൻ ഈസ് യൂസ്ഡ് ടു ഒബ്റ്റെയിൻ static calibration is used to obtain static characteristics, and the static characteristics of an instrument includes accuracy, precision, resolution, repeatability, reproducibility, static error, sensitivity, and drift. Okay, these are the static characteristics of an instrument. Here in static characteristics, at a time instant, okay, or a unvarying data is measured. Okay, next one is dynamic characteristics. These characteristics which indicate response of the instruments that measure time varying quantities in which input varies with time and also output varies with time. Okay, in case of dynamic characteristics, we will be measuring response of the instruments that measure a time varying quantity. Okay, and also here input also varies with time, output also varies with time, and that this time varying input could be a step input, ramp input, or a sinusoidal input. And the dynamic characteristics of an instruments include measuring lag, fidelity, speed of response, dynamic error. Okay, these are the dynamic characteristics, and static characteristics are accuracy, precision, resolution, repeatability, reproducibility, static error, sensitivity, and drift. So we will discuss in detail about this. So static characteristics of an instrument. First one is accuracy. Accuracy is defined as degree of closeness or exactness of the measured value compared to the expected value of the quantity being measured. Accuracy is defined as a degree of closeness or exactness to the measured value. Okay. Manufacturers of an instrument also specifies the accuracy as the maximum amount of error which will be not exceeded. Okay. Manufacturer ഇപ്പം നമ്മുടെ റെസിഡൻസിനൊക്കെ വരുന്ന സമയത്ത് പ്ലസ് ഓർ മൈനസ് ദിസ് പെർസെൻറ്റേജ് എന്നൊക്കെ പറഞ്ഞിട്ട് എറർ കാണിക്കില്ലേ. സോ മാനുഫാക്ചർ ഓൾസോ ഇൻഡിക്കേറ്റ്സ് ദ എറർ, ഹൗ മച്ച് എറർ it can be like that. So that is how the manufacturer is specifying the accuracy. So manufacturers of instruments also specifies accuracy as the maximum amount of error which will not be exceeded. Therefore it can be termed as conformity towards truth. So accuracy can be termed as conformity towards truth. Okay, so if accuracy of a plus or minus 1% is specified for a 100-volt voltmeter, the true value of the voltage lies between 99 volt and 101 volt, with the maximum error for any observed value or reading not exceeding plus or minus 1 volt. That is what it will be meaning. Plus or minus 1% means for a 100-volt voltmeter, the true value will be lying between 99 volt and 101 volt. Next one is precision. Precision means sharply or clearly defined. How sharply or clearly defined? That is what precision means. It is a measure of degree up to which repeated readings in a group of measurements are similar. ഒരു ഗ്രൂപ്പ് ഓഫ് റീഡിങ്സ് റിപ്പീറ്റഡ് റീഡിംഗ് എടുത്ത് അതിൽ എത്രത്തോളം സിമിലാരിറ്റി വരുന്നു അതാണ് പ്രിസിഷൻ. ഓക്കെ, ആൻഡ് ദ ഇൻസ്ട്രുമെന്റ് മെഷേർഡ് ഷുഡ് ബി ഇൻ സെയിം കണ്ടീഷൻസ്. ഓക്കെ, സെയിം condition should be same. Okay, precise reading need not to be accurate or vice versa. Precise reading should not be required to be accurate, and also an accurate reading should not be required to be precise. Okay, example, a voltmeter which having high degree of precision, which is finely divided, incredibly sharp pointer also can measure voltage to a value of 1 by 1000th of a volt, but the zero adjustment of the voltmeter is not accurate. So here voltmeter is highly precise but not accurate. അതായത് a voltmeter ഒരു voltmeter അതിന് 1 by 1000 times of volt വരെ അതിനെ point ചെയ്ത് നിൽക്കാൻ പറ്റുന്നു. So that voltmeter is a highly precise voltmeter. But here initially zero adjustment of that voltmeter is not made. Zero adjustment of that voltmeter not made means it will be not that much accurate. So here this voltmeter is precise but it is not accurate. Okay. Next one is resolution. Resolution is defined as smallest change in the measured quantity to which an instrument will respond. ഒരു ഇൻസ്ട്രുമെന്റ് ഉണ്ടാവുന്ന സ്മോളസ്റ്റ് ചേഞ്ച് സോ ദാറ്റ് ദ ഇൻസ്ട്രുമെന്റ് ഈസ് റെസ്പോണ്ടിങ് ടു ദാറ്റ് ദ ചേഞ്ച്. ഓക്കെ, ദ നീഡിൽ ഓഫ് ഇൻസ്ട്രുമെന്റ് വിൽ ഷോ നോ ഡിഫ്ലക്ഷൻ അൺലെസ് ചേഞ്ച് ഈക്വൽ ടു ഇസ് റെസൊല്യൂഷൻ ഈസ് ആക്ടിവേറ്റഡ് ഇൻ ഇൻപുട്ട്. അതായത് ഇൻപുട്ടിൽ ഒരു മിനിമം ഇൻപുട്ട് നമ്മൾ കൊടുക്കണം, എന്നാലേ ആ ഇൻസ്ട്രുമെന്റ് ഔട്ട്പുട്ടിൽ ഒരു deflection കാണിക്കത്തുള്ളൂ. Okay, that is resolution. For example, consider a 200 volt voltmeter in which needle shows a deflection or reading change from 0 only when minimum input of 1 volt is given. Okay, അതായത് 200 വോൾട്ട് ഉള്ള ഒരു വോൾട്ട് മീറ്റർ ഉണ്ട്. ആ 200 വോൾട്ട് ഉള്ള ഒരു വോൾട്ട് മീറ്ററിൽ റെസൊല്യൂഷൻ 1 വോൾട്ട് ആയി വിചാരിച്ചു. അപ്പോൾ ഇൻപുട്ടിൽ നമ്മൾ 1 വോൾട്ട് കൊടുത്താൽ മാത്രമേ ഔട്ട്പുട്ടിൽ ഒരു ചേഞ്ച് വരത്തുള്ളൂ. ഓക്കെ, അതായത് ഇൻപുട്ടിൽ ഇപ്പം നമ്മളൊരു 0.5 വോൾട്ട് കൊടുത്തു വിചാരിക്കുക, ഔട്ട്പുട്ടിൽ റീഡിങ്ങിൽ ഒരു മാറ്റം വരില്ല. സോ മിനിമം 1 വോൾട്ട് കൊടുക്കണം ഔട്ട്പുട്ടിൽ എന്തെങ്കിലും ചേഞ്ച് വേണമെങ്കിൽ. ഓക്കെ, that is, this instrument cannot be used to measure 50 millivolt because its resolution is 1 volt. That is, there will be no effect on instrument for any input or change in input less than 1 volt. 1 volt 1 വോൾട്ടിന് മേലെയോ ചേഞ്ച് വന്നാൽ മാത്രമേ അതിൻ്റെ ഔട്ട്പുട്ടിൽ ഡിഫ്ലക്ഷൻ മീറ്ററിൽ എന്തെങ്കിലും ചേഞ്ച് വരത്തുള്ളൂ. ദാറ്റ് ഈസ് റെസൊല്യൂഷൻ. ഹിയർ റെസൊല്യൂഷൻ ഈസ് made as 1 volt in this example. Okay, next one is repeatability, also termed as test retest reliability. Okay, it is the variation of scale reading when the input is applied randomly. Okay, that is repeatability. It provides closeness with which one can measure a given input value repeatedly. That is, repeatability gives closeness with which one can measure a given input value repeatedly. ഒരു given input value repeatedly നമ്മൾ മെഷർ ചെയ്യുന്ന സമയത്ത് അതിൻ്റെ എത്രത്തോളം ക്ലോസ്നെസ് it is providing, that is repeatability. Sometimes repeatability is also termed as inherent precision of the measured equipment. It is also related to somewhat related to precision. Okay, ഒരു same it provides closeness with which one can measure a given input value repeatedly. ഒരു given input value വീണ്ടും വീണ്ടും റിപ്പീറ്റ് ആയിട്ട് അതിനെ മെഷർ ചെയ്യുന്നു, അത് എത്രത്തോളം അതിൻ്റെ ഔട്ട്പുട്ട് ക്ലോസർ ആണ് എന്ന് കാണിക്കുന്നതാണ് റിപ്പീറ്റബിലിറ്റി. ഇഫ് എൻ ഇൻപുട്ട് ഓഫ് എ കോൺസ്റ്റന്റ് മാഗ്നിറ്റ്യൂഡ് ഈസ് അപ്ലൈഡ് randomly, the output must be same, otherwise the instrument is said to have a poor repeatability. അതായത് ഒരു ഓൾമോസ്റ്റ് സെയിം ആയിട്ടുള്ള കോൺസ്റ്റന്റ് മാഗ്നിറ്റ്യൂഡുള്ള ഇൻപുട്ട് നമ്മൾ അപ്ലൈ ചെയ്യുന്നു different times, and the output, whenever it is producing an output, it should be almost same. If it is almost same, we'll be telling that it is having a high repeatability. If it is not same, we'll be telling it is having a poor repeatability. Okay, the figure shows a relation between the input and output with the plus or minus repeatability. This is the actual value that is given here, and it is having a repeatability, that is the value measured the output measured should be having output value closer to this measured value. Okay, if it is closer to this measured value, we will be telling it is having a higher repeatability. If it is coming beyond that, we will be telling it will be having a poor repeatability. Next one is reproducibility. Measure of closeness, എല്ലാ ടേംസും ക്ലോസ്ലി റിലേറ്റഡ് ആണ്, ചെറിയ ചെറിയ ഡിഫറൻസ് വരുന്നുള്ളൂ. ദാറ്റ് യു ഹാവ് ടു നോട്ട് ഇറ്റ് ഡൗൺ. ഓക്കെ, next one is reproducibility. It is the measure of closeness with which one can measure a given input repeatedly when the input is applied constantly. Okay, it is the measure of closeness with which one can measure a given input repeatedly when the input is applied constantly. Constantly ഒരു given input അപ്ലൈ ചെയ്തുകൊണ്ടിരിക്കുകയാണ്, അത് എത്രത്തോളം അത് റീപ്രൊഡ്യൂസ് ഔട്ട്പുട്ടിൽ റീപ്രൊഡ്യൂസ് ചെയ്തു വരുന്നു, അതാണ് റീപ്രൊഡ്യൂസിബിലിറ്റി. ഓക്കെ, ഇറ്റ് ഈസ് മെഷർഡ് ഓവർ എ given period of time. It indicates steady state response of a instrument. It indicates steady state response of instrument. The instrument should have a good reproducibility, which is possible only when the output reading of the instrument remains the same when an input with a constant magnitude is applied continuously over a period of time. Over a period of time, a continuous input we are applying, and the output reading also remains almost same. Okay, that is what reproducibility. Next one is static error. Error is defined as the difference between the measured value and the true value. That is the error. And if it is not possible to measure the true value of the quantity, so best measured value is used as a true value. Okay, if it is not possible to measure true value of a quantity, we will be taking best measured value as a true value. The error may be equal or less than the value given by the accuracy. Okay, error will be always equal or less than the value given by the accuracy. Okay, in accuracy it will be giving plus or minus 1% like that. So error will be always less than or equal to the value given by the accuracy for a particular instrument. When the error difference is constant, the error is said to be static error. When that error difference it is constant, we will be telling it is a static error. Next one is sensitivity. It is defined as ratio of change in output with respect to change in input of the instrument. Change in output with respect to change in input of the instrument. Example, consider a voltmeter. If the input voltage changed by 0.2 volt, then the output reading also should be changing by 0.2 volt. Sensitivity is expressed as delta V0 by delta Vi. Delta V0 means change in output voltage divided by change in input voltage. Okay, for example, and change in output divided by change in input represents how truly one instrument responds to a change in input. How truly an instrument responds to a change in input. K, which is defined as sensitivity, which is equal to delta Q0 by delta Qi, where Q0 and Qi are the value of the output and input signals respectively. Next one is drift. Drift is defined as gradual shifting indication of an instrument. Gradual shifting indicating of a instrument. Okay, that is defined as instrument over a period of time during which true value of the quantity does not change. That is, drift is defined as gradual shifting indication of the instrument. It will be having gradual shifting over a period of time during which true value of the quantity does not change. It is categorized into three: zero drift, span drift, and Sonville drift. In zero drift, same amount of shifting in the wall calibration is termed as zero drift. It is also called as calibration drift. You can see here, this is the normal characteristics, and the same amount of shifting is made here. You can see this is the characteristics with the zero drift. The normal characteristics is shifted here, and you can see here the same amount of shifting in wall calibration. Okay, and it occurs mainly due to slippage, warming of the electronic circuit, or if an initial adjustment of the instrument is not made. Because of this it is happening. And next one is span drift. Span drift means which increase gradually with the deflection of the pointer. It increases gradually with the deflection of the pointer. You can see this is the normal characteristics. As the measuring increases, you can see here the span shift is increasing. This is the characteristics with the span shift. Okay. The combined zero and span drift is shown here. This is both when the span shift and the zero shift both are combined, it will be coming like this. This is the normal characteristics, and this is the characteristics with the zero and span drift. Okay. Next one is zonal drift. This drift occurs only in a particular zone. In a particular zone only that the drift will be occurring. It may due to mechanical vibration, wear and tear, electric and magnetic fields, mechanical stress developed in some parts of the instruments and system. Okay, it is not this zonal drift is not happening everywhere. It is happening in a particular zone and or particular parts of the measuring instruments. That is it may be due to mechanical vibration, wear and tear, electric and magnetic fields, mechanical stress developed in some parts of the instruments. Next one is dynamic characteristics. In dynamic characteristics, we have already seen അതായത് ടൈം വേരിങ് ക്വാണ്ടിറ്റീസ് മെഷർ ചെയ്യുമ്പോൾ ഉണ്ടാകുന്ന ക്യാരക്ടറിസ്റ്റിക്സ് ആണ് ഡൈനാമിക് ക്യാരക്ടറിസ്റ്റിക്സ്. വേറെ സ്റ്റാറ്റിക് ക്യാരക്ടറിസ്റ്റിക്സ് മീൻസ് സ്റ്റഡി സ്റ്റേറ്റ് ഓർ നോൺ വേരിങ് കേസിലുള്ള ക്യാരക്ടറിസ്റ്റിക്സ് ആണ്. ഓക്കെ, സോ ക്യാരക്ടറിസ്റ്റിക്സ് വിച്ച് ഇൻഡിക്കേറ്റ്സ് ദ റെസ്പോൺസ് ഓഫ് ഇൻസ്ട്രുമെന്റ്സ് that measure time varying quantities in which input varies with time and also output also varies with time. That is called as dynamic characteristics. Time varying input could be a step, ramp or sinusoidal input. Various factors such as mass, fluid capacitance, thermal capacitance or electric capacitance causes slowness in the instrument that are used to measure time varying quantities. Time varying quantities ഈ ഒരു factors ഒക്കെ included ആണ്. So it will be making that instrument to respond little bit slow. This results delay of the response of the instruments with respect to change of the measured variables. Some delay may arise when the instrument is waiting for some other reaction to occur. After that only it will be responding to that. So it is important to study the dynamic behavior of the instruments. Dynamic characteristics include measuring lag, fidelity, speed of response and dynamic error. Dynamic characteristics of device depends on order of differential equation. It is depending on order of differential equation also. First, for a first order instrument, first order instruments are characteristics by one parameter which is called as time constant tau of the system, and it is generally represented by tau y dash plus y, which is equal to x of t, where x of t is the function of input, time function of input, where y is the output of the system. Okay, lower the time constant means faster the response and minimum error. Okay, so for a first order instrument it is characterized only by one parameter which is called as time constant tau. Okay, then second order instruments, a second order instrument is characterized by two constants. One is natural response omega n and the damping ratio theta of the instrument, and it is represented by 1 divided by omega n square into y double dash plus 2 zeta divided by omega n into y dash plus y, which is equal to x of t, where omega n is expressed in radians per second, and the theta theta is a non-dimensional quantity which indicates relative stability of the system. Now we are coming to the dynamic characteristics of the instruments. One is measuring lag. Measuring lag means any change in measured quantity causes delay or retardation in the response of the instruments. Okay, അതായത് ഇപ്പോൾ ഒരു മെഷറിംഗ് ക്വാണ്ടിറ്റിയിൽ ഒരു ചേഞ്ച് ഉണ്ടായി കഴിഞ്ഞാൽ അതൊരു ഡിലേ ഉണ്ടാകും. ഓക്കെ, അതാണ് ഈ മെഷറിംഗ് ലാഗ് എന്ന് പറയുന്നത്. ഓക്കെ, ആൻഡ് ദിസ് മെഷറിംഗ് ലാഗ് ഈസ് ഓഫ് two types. One is retardation type, when change in measured quantity occurs and the instruments responds immediately, it is called as retardation type. And another one is time delay type, in that the instrument responds after a dead time after the input is applied. Okay, the instrument responds later after a dead time after the input is applied. Here the quantity be measured if varies very quickly, the performance of the system will be adversely affected due to this dead time. Okay, അതായത് ടൈം ഡിലേ ടൈപ്പ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഇപ്പോൾ ഒരു ഇൻപുട്ടിൽ ഒരു ചേഞ്ച് ഉണ്ടായി, അത് കഴിഞ്ഞ് കുറേ കഴിഞ്ഞ് കഴിഞ്ഞാലേ അതിൻ്റെ റെസ്പോൺസ് വരത്തുള്ളൂ. സോ ഹിയർ ഇൻപുട്ടിൽ ചേഞ്ചസ് ക്വിക്ലി മാറിക്കൊണ്ടിരിക്കുകയാണെങ്കിൽ ഈ in time delay type it is very difficult to plot the desired output, because it is affecting by the dead time. Dead time കഴിഞ്ഞാൽ മാത്രമേ the input output ലേക്ക് വരത്തുള്ളൂ here. So it will be adversely affecting the system. Okay, if the input is continuously quickly vary. Next one is fidelity. Fidelity means the quantity of the quality of reproducing faithful value is known as fidelity. Faithful value means ഒരു ടൈം ഡിലേയിങ് കണ്ടീഷനിൽ faithful value reproduce ചെയ്യുന്നതിനാണ് fidelity എന്ന് പറയുന്നത്. It is defined as ability of instrument to indicate the changes in measured quantity without the dynamic error. ഡൈനാമിക് എറർ ഇല്ലാതെ നമുക്ക് എത്രത്തോളം ഫെയ്ത്ത്ഫുൾ ആയിട്ട് നമുക്ക് ഔട്ട്പുട്ട് റീപ്രൊഡ്യൂസ് ചെയ്യാൻ പറ്റും, അതിനെയാണ് ഫിഡലിറ്റി എന്ന് പറയുന്നത്. Okay, next one is speed of response, the quickness with which an instrument responds to changes in the measured quantity. Quickness with which the instruments responds to the changes in the measured quantity, that is speed of response. Next one is dynamic error. It is also called as measurement error, defined as difference between the true value of the time varying quantity and the value indicated by the measurement of the system in absence of static error. Okay, dynamic error means dynamic error will be the error for a time varying quantity, and it is defined as the difference between the true value and the measured value in a time varying case. Okay, that is dynamic error. Okay, next one we are discussing about Wheatstone's bridge. Okay, so what is Wheatstone's bridge? It is a electrical circuit used to measure an unknown electrical resistance by balancing two legs of the bridge circuit, one leg of which include unknown component. One leg unknown component ഉണ്ടാവും, എന്നിട്ട് ആ ബ്രിഡ്ജിനെ ബാലൻസ് ചെയ്യാം. അതാണ് Wheatstone's bridge. Okay, it is mainly used for measurement of electrical resistance. The major advantage is that it will produce accurate measurements, and the operation is similar to that of a potentiometer. And this is the circuit of a Wheatstone's bridge. You can see here it consists of a 4 resistance arms forming a closed circuit, and it is having a DC source of current applied to the opposite junction, and here you can see a current deflector or galvanometer is connected in the other two junctions. Okay, to A and B, that EMF is applied, and the junction C and D is connected to a galvanometer. Okay, and the resistance R1, R2, R3, R4 is placed, and the current flowing across R1 is I1, across R2 is I2, across R4 is I4, and this across R3 is I3. Okay, and Wheatstone's bridge circuit is extensively used for measuring component values such as R, L, and C, resistance, inductance, and capacitance. Okay, and next one is measurement of resistance using Wheatstone bridge. Wheatstone bridge is the most accurate method available for measuring resistance and is popularly used in laboratory. The source of EMF and switch is connected to points A and B. Here you can see point A and B, source of the EMF is connected, and while a sensitive current indicating meter galvanometer is connected to the point C and D. To the point C and D, galvanometer is connected. Okay, the galvanometer is a sensitive microammeter with 0 central scale. It will be having 0 central scale. When there is no current through galvanometer, the galvanometer pointer rests at 0. Okay, mid scale. When the current DC is there in one direction, it causes pointer to deflect in one side, and if current is in opposite direction, it will be making that pointer to deflect in opposite direction. So based on the current flowing across the galvanometer, it will be deflecting into both sides, and if no current is flowing through galvanometer, it will be pointer will be resting at 0. Okay, when the path is closed, the current flow and it divides into two arms at point A, that is I1 and I2. Okay, when path is closed and the EMF is applied, you can see the current will be flowing coming to path A and it will be divided into I1 and I2. Okay, I1 and I2. The bridge is balanced when there is no current through the galvanometer, or when potential difference across point C and D are equal. Okay, when bridge is said to be balanced when no current is flowing across the galvanometer, that is the galvanometer reading should be 0 if bridge is balanced. Okay, so that means the potential difference at point C and D. Point C and D only that galvanometer is connected, so potential difference between C and D should be same, so that the galvanometer reading will be 0. Okay, to obtain the bridge in balance condition from figure, I1 R1 should be equal to I2 R2, so that both the potential across C and D will be same. I1 R1 should be equal to I2 R2. Okay, which is equal to equation number 1. For galvanometer current to be 0, the following condition should be satisfied, that is I1 should be equal to I3, I1 should be equal to I3 and I2 should be equal to I4. Then I1 equal to I3 should be equal to E divided by R1 plus R3 is the potential applied here. I1 equal to I3, which is equal to E divided by R1 plus R3. Okay, similarly, which is equation number 2, then I2 which will be equal to I4, which should be equal to E divided by R2 plus R4, which is equation number 3. So substituting this 2 and 3 in 1 for I1 and I2, we will be getting E into R1 divided by R1 plus R3, which is equal to E into R2 divided by R2 plus R4. Solving, we will be getting R1 R4 equal to R2 R3, that is R4 is equal to R2 R3 divided by R1. So this is the equation of bridge to be balanced. Okay, this is the equation of the bridge to be balanced. In practical Wheatstone bridge circuit, at least one of the resistance is made adjustable to permit balance. One of the resistance will be adjusting, and based on that adjusting value, we will be balancing the bridge. So the main advantage of this Wheatstone bridge is result not depending on the calibration characteristics of the galvanometer. It is not depending on the calibration characteristic of the galvanometer and also due to null deflection method used, accuracy and sensitivity is higher. For deflection instruments, accuracy and sensitivity is high. So due to that null deflection method, accuracy and sensitivity is high in case of Wheatstone bridge. And also source EMF and inaccuracies due to source fluctuation does not affect the balancing of the bridge. And the disadvantages are, it is not applicable for a higher resistance, because as we are using higher resistance, temperature will increase. Due to that increase in temperature, the resistance value may change. Excessive currents may generate heat, which may cause permanent change in the resistance. And also resistance used must be having a very precise tolerance up to 1% or 0.1%. Here, what all the resistance we are using, it should be more precise, so that the cost will be high. Okay, that is all about Wheatstone bridge. Now we are coming across SCHERING's WEIN bridge. Sorry, Maxwell's WEIN bridge. Okay, so Maxwell's WEIN bridge is a modification of a WEIN bridge used to measure unknown inductance with the low Q factor value in terms of calibrated resistance and capacitance. Okay, so in WEIN bridge we have seen it is used for measurement of resistance. Here in Maxwell's WEIN bridge we'll be using it for the measurement of inductance, but here one case is there, that inductance should be having low Q factor values. Advantage of this method is that inductance is measured in terms of high quality and almost loss free capacitor. Here the capacitor used here is a loss free capacitor. Okay, so we will be getting that inductor measurement accurately. And also bridge can measure wide range of inductance with the Q factor less than 10. Okay, Q factor should be less. Q factor should be less, and it should be less than 10. And Maxwell's WEIN bridge basically constructed by resistance, inductance, and capacitance. Okay, so generally AC bridge is shown here. You can see instead of resistance, capacitance, we are taking it as impedance Z1, Z2, Z3, Z4. For this, this is an AC bridge. Maxwell bridge is also an AC bridge. Okay, so for this bridge to be balanced condition, I1 Z1 plus I1 Z1 should be equal to I2 Z2. Question number 1. Similarly, what we have seen in WEIN bridge, and also I1 should be equal to I3. I1 should be equal to I3, and which should be E divided by Z1 plus Z3, and I2 should be equal to I4, which should be E divided by this is Z2 plus Z4. Okay, so that is equation number 2 and 3. Substituting equation number 2 and 3, I1 and I2 in 1, will be getting E into Z1 divided by Z1 plus Z3, which is equal to E into Z2 by Z2 plus Z4. So solving, we will be getting Z1 Z4, which is equal to Z2 Z3. And for a AC bridge, it will be having phase changes. So that also we are including here. Z1 into angle theta 1 into Z4 into angle theta 4, which is equal to Z2 into angle theta 2 into Z3 into angle theta 3. So here we are taking the magnitude part and phase part separately. Z1 Z4 into phase angle theta 1 plus theta 4, which is equal to Z2 Z3 into phase angle theta 2 plus theta 3. Okay, so the condition for balancing here for AC bridge is Z1 Z4, which should be, that is, we will be equating both magnitude part and phase part. So Z1 Z4 should be equal to Z2 Z3. That is one condition. And another condition is theta 1 plus theta 4 should be equal to theta 2 plus theta 3, phase angle part. Okay, so Maxwell WEIN bridge and also Maxwell bridge is of two types. One is Maxwell's inductance bridge, and also Maxwell's inductance capacitance bridge, or Maxwell's WEIN bridge. Okay, Maxwell's bridge is of two types. One is Maxwell's inductance bridge, and another one is Maxwell's inductance capacitance bridge, or Maxwell's WEIN bridge. Okay, so first we will be going to see to find inductance and resistance using Maxwell's inductance bridge. See, Maxwell's inductance bridge is there, and also Maxwell's inductance capacitance bridge is there. So this is the circuit for Maxwell's inductance bridge. Here you can see in this arm to the junction A and C, the source is connected, and junction B and D is connected to a deflection meter. And you can see here in this arm resistant R1 and inductor L1 is present, and here R3 is present. In this arm R2 and L2 is present, and here R4 is present. Okay, so we have to find here R1 and L1. Okay, so at balance condition, we know Z1 Z4 is equal to Z2 Z3. Z1 Z4, which is equal to Z2 Z3. Okay, so here Z1 we can write as R1 plus J omega L1. Okay, Z1 can be written as R1 plus J omega L1. Z2 can be written as R2 plus J omega L2. Z3 equal to R3 and Z4 equal to R4. Okay, that we are writing, and substituting Z1, Z2, Z3, Z4 here, we will be getting R1 plus J omega L1 into R4, which is equal to R2 plus J omega L2 into R3. Okay, so simplifying, we will be getting R1 R4 plus J omega R4 L1, which is equal to R2 R3 plus J omega L2 R3. So equating the real and imaginary part. Real part, if you are equating, we will be getting R1 R4, which is equal to R2 R3. R1 R4, which is equal to R2 R3. From that we will be getting R1 equal to R3 divided by R2 by R4. And also creating imaginary part, we will be getting omega R4 L1 which is equal to omega L2 R3. Omega omega cancel, R4 L1 equal to L2 R3. From that L1 we are getting L2 divided L2 into R3 divided by R4. So these are the expression for resistance and inductance in case of Maxwell inductance bridge. So thus we got the expression for the resistance and inductance for Maxwell's inductance bridge. Now we are going to find the inductance and resistance for Maxwell-WEIN bridge or Maxwell inductance capacitance bridge. So the circuit for the Maxwell inductance capacitor bridge is given here. That is similarly like previously, across junction A and C source is applied, and across junction P and D deflection meter is placed. Okay. And in the sum R1 and L1 is placed, and here R2 is placed, here R3 is placed, and here capacitance and resistance is made parallel. Okay, capacitance and resistance is made parallel here. Okay, this is about Maxwell's inductance capacitance bridge. So we'll be deriving the expression for the resistance and inductance R1 and L1 here. Okay, so here at balance conditions Z1 Z4 should be equal to Z2 Z3. So here Z1 we can write as R1 plus j omega L1. Okay, Z2 is equal to R2, Z3 equal to R3, and Z4 means R4 parallel to this capacitor, R4 parallel to this capacitor C4, that is R4 parallel to 1 divided by j omega C4. Okay, R4 parallel to 1 divided by j omega C4. So solve that we can put as R4 into 1 R4 into 1 divided by j omega C4 divided by R4 plus 1 divided by j omega C4. Solving we will be getting R4 divided by 1 plus j omega C4 into R4. Substituting Z1, Z2, Z3, Z4 in this balanced equation, we will be getting R4, solving we will be getting R1 R4 plus j omega L1 R4 which is equal to R2 R3 plus j omega C4 R4 R2 R3. Solving the real and imaginary part, we will be getting R1 equal to R2 R3 divided by R4, L1 equal to C4 R2 R3. So these are the expression for resistance and inductance for Maxwell's WEIN bridge. And also Q factor. Q factor, it is defined as XL divided by R. XL means we know that omega L1. XL means inductance across this L1. So XL it is we can return as omega L1, and R it can be written as R1. So when we are substituting R1 here and this L1 here, solving we will be getting Q factor which is equal to omega R4 C4. That is the Q factor expression here. Q factor expression for the Maxwell's WEIN bridge. Okay, and these are the expression for resistance R1 and L1. Okay, R1 is equal to R2 R3 by R4, and L1 is equal to C4 R2 R3. So these are the expression for resistance and inductance, and also Q factor for Maxwell's WEIN bridge. Okay, and the advantage of Maxwell's WEIN bridge is frequency does not appear in the final expression for L and R. Frequency is not there in the final expression. So L and R we can say it is independent of frequency, and another one is it is useful for wide range of measurement of inductance at inductor at audio frequencies. The major disadvantage of WEIN bridge is the variable capacitance placed here. Variable capacitance placed here, it is of high cost. Okay, so it is very expensive, and also bridge is limited to use between Q factor 1 and 10. If Q factor is less than 1, it can be used, and Q factor is more than 10 for inductor, it can be used. So Q factor for the inductor should be in between 1 and 10. Okay, that is another disadvantage of Maxwell's WEIN bridge. Now we are going to Scherin's bridge. Scherin bridge is extensively used for the measurement of capacitance. Okay, particularly insulators with the phase angles of nearly 90 degrees. It is used for measuring of capacitance with particularly for insulators with the phase angles of nearly 90 degree. Okay, and also in the standard arm of the bridge, a high quality mica capacitor is placed for general measurements, and for insulator measurements we are placing air capacitor in the standard arm. Okay, and for AC bridge, previously we have seen for AC bridge condition for balance bridge is Z1 Z4 which is equal to Z2 Z3, and theta 1 plus theta 4 which should be equal to theta 2 plus theta 3. So this is the circuit for SCHERING's bridge. Here you can see the source is applied across junction A and C, and across junction B and D the deflection meter is placed. And also here you can see capacitor and resistance is placed series. Here one capacitor C2 is placed, and here across BC a resistance R3 is placed, and here you can see a capacitor and a resistor is placed parallelly. Okay, so here Z1 we can written as Z1 we can written as R1 minus J XC1, R1 minus J XC1, and this minus J XC1 we can written as R1 plus 1 divided by J omega C1. Okay, R1 plus 1 R1 plus 1 divided by J omega C1. Okay, now Z2 Z2 we can written as minus J C2 J XC2, which can written as 1 divided by J omega C2. Okay, how this minus is going means downside if you put J square, 1 extra minus will be coming, so J and J will be cancelled, so it can be written as, and XC2 we can written as 1 divided by omega C2. Okay, so it will be equal to 1 divided by J omega C2. Then Z3 is equal to R3. Then in Z4 R4 is parallel to minus J XC4. Solving we will be getting as R4 divided by 1 plus J omega R4 C4. So these are the 4 impedance. So at balance condition Z1 Z4 which is equal to Z2 Z3. So substituting what all Z1 Z2 Z3 Z4 we got here, substituting we will be getting solving we will be getting J omega R4 C2 minus omega square R1 C1 C2 R4, which is equal to R3 J omega C1 minus omega square C1 R3 C4 R4. Here equating the real and imaginary part we will be getting. If we are equating the imaginary part we will be getting omega R4 C2 which is equal to omega C1 R3. Solving C1 which we are getting as R4 R3 into C2. Okay, and if you are equating the real part by cancelling omega square C1 and R4, we will be getting R1 C2 which is equal to R2 C4. From that R1 we are getting as R2 C4 by C2. So these are the expression for capacitance and resistance for a SCHERING bridge. Okay, so we have seen the resistance measurement using WEIN bridge, and the inductor measurement using Maxwell's inductance bridge and Maxwell's WEIN bridge, and now capacitance measurement using SCHERING bridge. So with this fourth module is concluded. So I hope everybody understood this. If any doubt, please get to me. So with this we are concluding this topic, concluding this module. So thank you everyone.